Hello, and welcome to our proposal for a lunar lander. We'll be starting with establishing need, moving over to defining the problem, go over all alternatives analysis, and then finally show our proposed concept. First, establishing the need. So ultimately, a key portion of going to the moon is needing a lunar lander. It is required in order to get to the moon, and that is a service we will provide. Specifically, we're going to design a parametric model of a lunar landing vehicle for the Artemis program that fulfills the requirements of moving crew and cargo. This facilitates commercial and international participation on the Artemis program. Now, why the moon? And the reason primarily is because our stakeholder, main one, is NASA, and they want to go to the moon as a part of their Artemis program, previously referred to as the Moon to Mars program. And they want to bring the humans back to the moon to stay. As a part of that, they're going to need a lunar lander, what they refer to as the human landing system. These contracts have already begun going out, first to SpaceX's Starship, and recently, the SLD stage of the proposals was just submitted this past November. NASA has chosen the moon as a first step for travel deeper into space, where we'll establish best practices for living on Mars based on lessons learned from living on the moon. As I mentioned before, our primary stakeholder is NASA, including the whole U.S. government. But also, other portions of Artemis are also our stakeholders, such as signers to the Artemis Accords, such as JAXA, ESA, and CSA, and commercial partners, such as Lockheed Martin and Northrop Grumman. Now, for the perspective of our stakeholders, specifically our government stakeholders, they will get a competitively priced and efficiently developed lunar lander. They will be directly supporting other commercial activities to create a lunar economy, which also helps our commercial stakeholders. We'll be providing jobs for communities nationwide. And we'll be providing an essential service for the Artemis program. This also, as an additional benefit to our commercial stakeholders, complements other essential services that those stakeholders are developing for the Artemis program, such as the Lunar Gateway facility that we will need to both dock with, going to and back from the moon. Referring to existing products, there's only two that are even under development with full funding to go to the moon. The Apollo lunar module existed way back when. It was much smaller than the current one. And the Artemis Starship human landing vehicle, which was recently funded and will be doing the landings for the beginning of the Artemis program. We also have the Perseverance rover on here as another landing vehicle that we can compare against, even though this one is strictly robotic.
Hi everyone, my name is Austin Boyle, and next I would like to discuss the problem and objective that we are trying to solve with our lunar lander. Our goal is to design something that is capable of carrying cargo and crew to the surface of the moon, and above all, we would like to do this safely, reliably, and affordably. We believe we can do this by accomplishing the following objectives. We would like to reduce the cost of delivering payload to the surface by reusing our lander. And next, we'd like to be able to refuel on the surface of the moon via ISRU technology. We'd like to become the primary provider for delivering payload on the surface of the moon. And next, we believe we can do this by managing our development costs by using existing technologies and integrating with existing launch vehicles and interfaces. I will discuss our high-level mission summary in the next slide. However, I would like to highlight some of our high-level constraints. Above all, we would like to do this cheaply by reusing existing launch vehicles and interfacing with standard berthing and docking ports. Our lunar lander must be able to deliver a payload and land on the surface of the moon, or else we are wasting time and we are wasting money. And above all, in the name of safety, we would like to communicate telemetry and stats at all times to ensure that we are having no off-nominal events. So taking a look at our ConOps, we can see a much closer detailed view of how we are planning to capture all of these goals. Starting in step 5, once we are inserted into lunar orbit, we would like to wait for an orbital rendezvous craft to approach the orbit of the moon, in which we will transfer payload and commodities. From there, we will descend to the lunar surface and begin our ground operations phase. On the lunar surface, we would like to service the lander, we would like to deploy payload and crew, and we would even like to pick up payload so we can return that to lunar orbit to return to Earth. After we complete this cycle a number of times, we would be able to dispose of this lunar lander back to Earth to remove to reduce the amount of space junk floating around. Our communication summary is very simple. During initial launch operations, we would like to be directly communicating with ground communications on Earth. When we are in lunar orbit and we are rendezvousing with a resupply craft, we would like to do so by directly communicating to receive low latency rendezvous data and telemetry for docking. During the descent phase through steps 8 to 12, we will be directly communicating with lunar infrastructure to ensure that we are experiencing a nominal trajectory and course. To complete all of these goals, we started breaking down the lunar lander into functional architecture and systems. Above all, our primary systems will require us to communicate, maneuver in space, navigate, interface with existing vehicles in space. We need to be able to survive the environment, provide life support for crew and precious cargo, and we need to be able to refuel. Next, I would like to hand it off to Joaquin to continue the presentation. Thank you.
So now that the needs and wants of our stakeholders have been identified through the QFD, we continue to establish value with our design by identifying the high-level requirements that our lunar lander must fulfill in order to meet these needs and wants. So you can see some of these high-level requirements here. Example ones being related to life support, launch conditions. There's additional ones related to structure, communications, etc. And once this requirements decomposition took place, we then began a physical decomposition of our lunar lander to identify what systems it needs to have in order to meet and satisfy these requirements. So you can see those systems listed here on the right. And of course, these are also very similar to the systems that have historically been used on lunar landers to meet the needs and wants of stakeholders in this sector.
Switching over to feasible alternatives. While developing our final design selection, we looked at several alternatives, which are presented here in the morphological matrix. The major subsystems we looked at were propulsion, life support, materials, power generation, communications, and attitude control, as well as measurement. And we also looked at things such as payload volume and the possibility of making our design strictly cargo or crew, or having capability to have both on board. And so on the right hand side are all the options we explored. Realizing that the massive subsystem is usually propulsion, we decided to analyze several types of propulsion subsystems in the market. The three we looked at were solid chemical, liquid fuel, and electrothermal. Looking at solid chemical combustion, we pulled thrust, ISP, and mass values from the solid rocket used in the Surveyor spacecraft. An advantage of solid combustion is the relatively simple design as far as fuel and oxidizer storage. However, the major disadvantage is the lack of controllability over the engine. Similarly, we gathered thrust, specific impulse, and mass data for the lunar module descent engine used in the Apollo lander, lunar lander, which utilized liquid fuel combustion. An advantage of liquid fuel is the vast flight heritage, and in comparison to solid, can be throttled and usually weighs less. Lastly, we looked at electropropulsion, specifically electrothermal. The example we looked at was a resistor jet used in the BSAT-2 satellite. It's an attractive option given its use of noble gases as propellant in terms of cost. However, given its low thrust, it's been limited to satellite applications, mostly due to limitations in the power processing unit. Given the three propulsion subsystems, we performed a topsys trade study to evaluate each alternative. And so the matrix we used to rank each alternative were thrust and technical readiness level, which were the highest in priority, followed by mass coming in second in terms of priority, and then lastly cost and specific impulse coming in last. Here is the result of our trade study performed based on the metrics described before. So liquid fuel combustion was selected as the best propulsion system given its high technical readiness level, specific impulse and thrust, and then solid combustion came in second, followed by electrothermal.
So now that our trade study has told us what the optimal propulsion system is for our design, we'd like to walk you through our concept proposal design, including it. So you can see here 3 different views of our proposed lunar lander, as well as some key highlighted points that we'd like to mention, starting with the one at the bottom, related, of course, from our trade study to our propulsion system being liquid fuel combustion. Our lunar lander will also have storage compartments where the propellant will be stored, as well as cargo. There will also be a habitable volume for the astronauts to be located in. The lunar lander will also have multiple attitude thrusters to help orient the lunar lander during landing, as well as from docking and berthing in space. And it will also have multiple configurations. Here you can see the landing configuration as an example. We have also begun preparation for verification and validation of our design. As part of that, a preliminary requirements verification matrix was created where each of the requirements related to our lunar lander were related to their specific success criteria. We have also begun identifying potential risks that our lunar lander will have, as well as the source of these risks, the likelihood that they are to occur, the consequence if they do occur, and their respective mitigation strategies. So an example I can go through is risk number 5, where, for example, the lunar lander does not withstand launch conditions. This will, of course, be a design-related risk that is quite unlikely to occur, but could be catastrophic if it does. And so to help mitigate this risk, we will perform various tests prior to launch on the lunar lander that are slightly more extreme than the maximum launch conditions possible to help ensure that it can survive any launch conditions. You can also see additional risks that we've identified here. And so in conclusion, we believe that our design is a good one, given, for example, the ISRU refueling on the lunar surface can help offer significant reductions in cost per kilo when delivering cargo or astronauts to the lunar surface. We have also specialized our design to be able to work in parallel with other launch vehicles and other vehicles to the moon. So for example, since our design is specialized in transporting cargo and crew from the lunar surface to low lunar orbit, it can also work in parallel with other vehicles which are more specialized with transporting cargo and crew from Earth to cislunar space, like is Starship. From our QFD comparison with other vehicles, we have also shown that our vehicle has superior performance. We are also smartly sized in the market, and we believe that by choosing us, not only will you have a good lunar lander, but it can also help stimulate further R&D in this sector, which will be crucial given the high interest in cislunar space as is moving into the future.